Hi there, so this video is going to be reviewing solving basic trig equations, and we're going to look at using a couple different methods in order to solve basic trig equations. So solving by inspection, solving graphically, which you can actually solve more complicated trig equations graphically, but then also using certain algebraic techniques like properties of equality, factoring, and then also using some of the fundamental trig identities that you should be familiar with. So we're going to first talk about solving by inspection. And whenever you're solving an equation by inspection, it means that you're looking at the equation and you're thinking what value would or values would make this a true statement. So for example, if we were solving the equation 3x equals to 27 by inspection, you go, okay, 3 times what would be equal to 27? And then you would think, okay, when x is equal to 9, this would be a true statement. So the solution would be x equals to 9. If you were thinking, oh, if I divide by 3 on each side of the equation, well, that's not solving by inspection. That's actually thinking about applying a property of equality. So when you're solving by inspection, you're just looking at the equation and thinking about what value or values would make it a true statement. So we're going to look at solving some basic trig equations first. So sine of x equals to positive 1/2 and cosine of x equals to negative 1/2. And positive 1/2 and negative 1/2 are both ratios from the unit circle. So we know that they're values that sine and cosine will be, and they're also more specifically values from the unit circle, where we can think about, visualize the unit circle in order to come up with the solutions. We are solving these particular equations over the interval from 0 to 2 pi, so just one rotation of the unit circle. So we can really just reference the unit circle here. We don't have to think about also coterminal angles yet. So sine of x equals to 1/2. I think, okay, well, sine is positive in quadrant 1 and quadrant 2. So we're going to have a solution from quadrant 1 and a solution from quadrant 2. The angle in quadrant 1 that would make this a true statement would be pi over 6. And then the angle that would make this a true statement from quadrant 2 would be 5 pi over 6. And then for cosine equals to negative 1/2, cosine is negative in quadrant 2 and quadrant 3. So the angle from quadrant 2 that would make this a true statement would be 2 pi over 3. And the angle from quadrant 3 would be 4 pi over 3. Okay, so just looking at these equations, thinking about unit circle, I know that those are the solutions. That's solving by inspection. Now, the idea behind solving graphically is here's a sketch of sine. And we can see from looking at the graph of sine that there are 2 points where sine would be equal to 1/2, and I have them in green. And the x values that correspond to those points we know are pi over 6 and 5 pi over 6. You can also think about solving this equation or coming up with the approximate solutions using your TI-84. And you can do that from creating a system of equations here. So if we had one equation, y equals to sine of x, and the other equation, y equals to 1/2, which is a horizontal line at y equals to 1/2. Okay, so drawing that. So you could graph both of those on your equation, both of those equations on your graphing calculator. You would want to be able to see both intersections in your window. So you'd want to adjust your window so that you could see both of those. Like I would probably have my window go from 0 to 2 pi, have my x scale go by maybe like pi over 6s or pi over 12s, and then my y min like -2, y max 2, so that you can see the points of intersection. And then you do you hit the second button, and then you hit the trace button. And then I believe it's number 5 is intersect. And then you're going to use the arrow keys and scroll the cursor that's blinking to as close to the point of intersection as you can. And in the bottom, it'll say left question mark and you hit enter. And then it'll say right question mark, you hit enter, and then guess question mark, and you hit enter one more time. So you hit enter 3 times, and it'll give you its approximation for the point of intersection, which would end up being, and for this particular equation, it would be an approximation of pi over 6. So it has some limitations, but if you could also use this technique to solve more complicated trig equations where you would maybe be getting an approximation anyways. But it's just another method to think about solving equations. But for something like when you have sine equals or cosine equals or tangent equals to a ratio from, is from the unit circle, it's usually easiest to just solve by inspection. So next we're going to look at solving the equation cosine of x equals to negative root 2 over 2. And negative root 2 over 2 is a ratio on the unit circle. So this is something we can solve by inspection. The difference in this example is that we're going to first solve over all real numbers. So we want to represent all of the possible solutions to this equation. And thinking about the graph of cosine oscillating between -1 and 1 from negative infinity to positive infinity, there's going to be infinitely many solutions. So the way that we approach this is we first think, okay, well, over cosine's fundamental period from 0 to 2 pi, there are going to be 2 angles that would make this a true statement. Cosine is negative in quadrant 2 and quadrant 3. So in quadrant 2, that angle would be 3 pi over 4. And then in quadrant 3, that angle would be 5 pi over 4. We want to include all of the coterminal angles to each of those angles. So to do that, I'm going to add 2 pi n to each of those angles. And then I need to define, so I can say or, and then I need to define n as an element of the integers. And you can write out where n is an integer, or you can use the shorthand, say n is an element of the integers. So that means that n can be 1, 2, 3, 4, 5, 0, -1, -2, -3, -4, and so on. So this statement represents all of the possible solutions, so all the solutions over all real numbers to that equation. We can use the general solution set, so the solution over all real numbers can also be known as the general solution set, in order to solve then over a specific interval. So like if we wanted to come up with the solutions from 0 to 2 pi, you could just come up with those values by inspection. But if you wanted to reference the general solution set, you could think, okay, well, if from this first equation, if I let n equal to 0, I would get x equals to 3 pi over 4. And then you go, okay, well, if we let n equal to +1, well, if we add 2 pi to 3 pi over 4, we're going to be outside of the interval that we're solving over. So we're done with that equation. If we let n equal to -1, we would also be outside of the interval. So then we can go over to this second equation and we go, okay, well, if we let n equal to 0 in this equation, we would get 5 pi over 4. And then the same thing happens where if we let n equal to 1, we would be outside of the interval. Now, if you were solving over a larger interval from like, I don't know, let's say -2 pi to 2 pi or 0 to 4 pi, that's where thinking about applying different values of n would maybe be helpful for coming up with your solution set. But something like this would probably make the most sense to just solve by inspection. Okay, so if we wanted to solve the equation sine of x equals to 0, now 0 is a value from the unit circle. This equation is different from the previous examples because something is happening to the x, right? It's not just sine of x equals to 0 or sine of theta equals to 0. It's 2x. So we first want to come up with the solutions for 2x. We want to think about what could we replace 2x with that would make sine equal to 0. And we want to come up with the general solution set first. So we're going to have 2x, okay, or equals, or 2x equals. And then we think, okay, well, sine would be equal to 0. Whenever we take sine of 0, we get 0, right? So when 2x is equal to 0, but also whenever 2x would be equal to pi, right? If we replaced 2x with pi, sine of pi is 0. And then we need to include all of the coterminal angles to both of those angles. So to the angles that are between 0 and 2 pi, 2 pi would also be where sine would be equal to 0. But notice over here, if we let n equal to 1, 2 pi would be included. So that's okay. Then we want to divide each part of each of these equations by 2. So we would get x equals to pi times n, or x equals to pi over 2 plus pi times n. And again, we need to define n as an element of the integers. So this ends up being our general solution set, our solutions over all real numbers. And then when we want to come up with the solutions from 0 to 2 pi, not including 2 pi, we can do the same thing. We can either solve by inspection or, and especially for when there's more complicated arguments, I think it's helpful to come up with the general solution set first and then just assign values to n. So like if we let n equal to -1, negative pi, we're outside of the solution, the interval that we're solving over. If we let n equal to 0, well, 0 is included in this interval. And then we can think about letting n equal to 1, and that would give us pi. If we let n equal to 2, that's 2 pi, which is outside of the interval, right? 2 pi is not included. So then we're done with that equation. We can go over to the second one. If we let n equal to 0, we would get pi over 2. And if we let n equal to 1, we would get 3 pi over 2. And if we let n equal to 2, well, then we're outside of the interval. So these are our 4 solutions over the interval from 0 to 2 pi. Okay, so -2 pi to 0, that's a slightly different interval. So same sort of process. We go back to our general solution set and we can go, okay, well, if we let n equal to -2, well, -2 pi is not in the interval. Well, let's let n equal to -1. So then we would get negative pi, and if we let n equal to 0 in that equation, we'd get 0. If we let n equal to 1, we're at pi, which is outside of the interval. So then we're ready to come over to the second equation. I think, okay, well, if we let n equal to -2, well, pi over 2 minus 2 pi, that's pi over 2 minus 4 pi over 2 would be -3 pi over 2. And if we let n equal to -1, pi over 2 minus 2 pi over 2, right, minus pi would be -pi over 2. And if we let n equal to 0, well, then we have gone too far. Oops, I meant to bring that, sorry, to bring that down here. If we let n equal to 0, then we are outside of the interval. So those would be our solutions from -2 pi to 0. Okay, solving the equation tan of 2x equals to 1. Similar strategy. Coming up with the general solution set first. 1 is a ratio for tangent on the unit circle. So we come up with the general solution set basically using inspection. So tangent is positive in quadrant 1 and quadrant 3. So, but however, the fundamental period of tangent is pi. So we can actually just think about the angle from quadrant 1 or one of the two quadrants. So either quadrant 1 or quadrant 3, that would make this a true statement. So I'm just going to use pi over 4. And then we can think about adding multiples of pi. So I'm going to define n as an element of the integers. Because notice, if I were to add pi, so if I let n equal to 1 here, pi over 4 plus pi would be 5 pi over 4, which would be the angle from quadrant 3. That would make that a true statement. And then we need to finish isolating x. We can just think about dividing by 2. So we'd get pi over 8 plus pi over 2n. Where n is an element of the integers. So this would be our general solution set. And then we can use our general solution set to come up with our solutions from negative 2 pi to 2 pi. Okay, so if we were to let n equal to, how about negative 4? Because that would be, we'd end up subtracting by 2 pi. So if we let n equal to negative 4, that would be pi over 8 minus 2 pi, which would be minus 16 pi over 8, which would be negative 15 pi over 8. So that was letting n equal to negative 4. So then if I let n equal to negative 3, well, pi over 8 minus 3 pi over 2 would be minus 12 pi over 8. So that would be negative 11 pi over 8. Okay. And then if we let n equal to negative 2, that would be minus pi. So minus 8 pi over 8 would be minus 7 pi over 8. And then minus 1, so minus pi over 2 would be minus 4 pi over 8, so minus 3 pi over 8. And I did minus negative 1. Okay, so 0 would be pi over 8. And then if I let n equal to 1, that would be plus pi over 2, which would be plus 4 pi over 8, which is 5 pi over 8. And then if I let n equal to 2, that would be plus pi, which would be plus 8 pi over 8, or 9 pi over 8. And if I let n equal to 3, that would be plus 12 pi over 8, which would be 13 pi over 8. And I know that 16 pi over 8 would be 2 pi, so we're still okay. And then if we let n equal to 4, that would be adding 2 pi, and we would be outside of the interval. So those are all of our solutions from negative 2 pi to 2 pi. And it was helpful having the general solution set in order to come up with those solutions on that interval. So it's just important to recognize that unless the domain is explicitly stated, you're solving for overall real numbers. Like you're coming up with the general solution set. So again, something like this, root 2 over 2 is on the unit circle. I think, okay, well, cosine is positive in quadrant 1 and quadrant 4. The angle from quadrant 1 that would make this a true statement would be pi over 4, and then I need to add 2 pi n to include all of its coterminal angles. And then the angle from quadrant 4 that would make this a true statement would be 7 pi over 4. I need to add all those coterminal angles. And don't forget to define n as an element of the integers. Okay, so negative root 3 is a ratio for tangent on the unit circle. Coming up with the general solution set, I'm solving for what 2x would be equal to first. So tangent is negative in quadrant 2 or quadrant 4, so I can come up with a quadrant 2 or quadrant 4 angle that would be equal, tangent would be equal to negative root 3. So I'm going to use 5 pi over 6 and then add pi times n. Then thinking about dividing by 2, we would have 5 pi over 12 plus pi over 2n, where n is an integer. And you can always double check by assign values to n and think about plugging back into the equation. Okay, sometimes we have to use some algebra in order to solve a trig equation, usually to isolate the trig function. So in this case, for this equation, we would want to subtract by 1 first. So we'd get 2 cosine theta equals to 1, and then divide by 2. So then to come up with the general solution set, we're thinking, okay, cosine's positive in quadrant 1 and quadrant 4. In quadrant 1, cosine would be equal to 1/2 at pi over 3. Oops. And then we need to add 2 pi n to include all of the coterminal angles. And then in quadrant 4, 5 pi over 3 would make that a true statement, or would be where cosine is equal to positive 1/2 and we add 2 pi n. So there's the general solution set, and then to come up with the solutions from 0 to 2 pi, we reference the first equation in the general solution set first. Let n equal to 0, and we'd get pi over 3. If we let n equal to 1, we'd go past the interval. And then in the second equation, we could let n equal to 0 again, and we get 5 pi over 3. That could also just be solved by inspection. Just looking at the equation and going, well, where's cosine equal to 1/2 on that interval? Okay, this is a quadratic-like equation. So we first think, well, does this factor? Right, to get the 2 sine squared, we'd have to have 2 sine and sine. And then factors of -1, we're going to have a positive one and a negative one. We need to get the negative sign for the middle term. So I believe that that's how it factors. 2 sine squared minus 2, yep, plus sine minus 1. There we go. So you get sine of x equals to -1/2, where sine of x is equal to 1 by the zero product property. And then we just need to come up with the general solution set to each of these equations. So in the equation where sine of x is equal to -1/2, I'm thinking, okay, sine is negative in quadrant 3 and 4. So the angle from quadrant 3 would be 7 pi over 6. And then adding 2 pi n to include all of the coterminal angles. Or x would be equal to 11 pi over 6 for the angle in quadrant 4, and add 2 pi n. And then for where sine is equal to +1, well, that's just going to be at, so looking at this equation, that would just be at pi/2. And then I'd add 2 pi n to include all of the coterminal angles. And don't forget to define n as an element of the integers. So that's our general solution set, those three statements, which are all sets of coterminal angles. And then to come up with the solutions from 0 to 2 pi, you can either just by inspection look at sine of x equals to -1/2 and go, okay, well, x would be 7 pi/6 or 11 pi/6. And then moving over to the other equation and thinking, okay, well, pi/2 would be the angle that would make sine equal to +1 from 0 to 2 pi. Or you could think about assigning values to n in our general solution set. Okay, sometimes we have to use trig identities in order to solve a trig equation. Sometimes you also end up using algebra. So something like this next equation, you look at it and you go, okay, well, everything's already in terms of sine and cosine. And if you're not sure, like, of another identity to use, you can always fall back on certain algebra techniques. You just have to be careful. So it's not obvious in this case. This equation actually can be solved just using trig identities. Like you could use the cofunction identities, but it uses some of the more complicated fundamental trig identities. So if it's not obvious to you, you could go, oh, well, what would happen if I square both sides of the equation? The only thing is when you square both sides of the equation as a technique to solve for a variable, you need to make sure you check for extraneous solutions, so solutions that don't make sense. An example that I always give is like if we start with an equation like x equals to 2, and then we think about squaring both sides, we get x squared equals to 4. Well, then if you're coming up with the solutions, like just looking at the equation, x squared equals to 4, you go, oh, well, x would be equal to ±2. But then in referencing that first equation, x is only actually equal to 2. -2 would be what we call an extraneous solution, a solution that doesn't make sense. So when you try squaring both sides of the equation as a method for trying to solve your equation, you just need to make sure that you check for those solutions that aren't actually solutions. So in this case, when we square both sides and think about multiplying the left-hand side out, that would be sine squared, and then it'll end up being -2 sine cosine and plus cosine squared equals to 1. Well, if you recognize then that sine squared plus cosine squared is equal to 1, and then if we were to subtract by 1 on both sides of the equation, well, now that we have 0 on one side of the equation and just a product on the other side, we could go, okay, well, sine of x is equal to 0 or cosine of x is equal to 0, and solve each of those equations. So if we were thinking about coming up with the general solution set, because no interval is stated here, I'm thinking, okay, well, sine is equal to 0 at 0 and plus 2 pi n to include all the coterminal angles, or at pi and plus 2 pi n. And then cosine would be equal to 0 at pi/2, and I add 2 pi n for all the coterminal angles, or at 3 pi/2. And we say where n is an element of the integers. But again, we have to check for extraneous solutions. So because each of these statements represents a set of coterminal angles, we can just think about assigning one value to n. So if I let n equal to 0 here, 0, and think about plugging 0 into the original equation. So sine of 0 is 0, cosine of 0 is 1, but then times this negative would be -1. Well, -1 is not equal to +1, so that's actually an extraneous solution. Or not actually part of the solution set. Here, if we let n equal to 0, so thinking about plugging in pi, well, sine of pi would be -1, cosine of pi, sine of pi would be 0, cosine of pi would be -1, but then times that negative would actually be +1. So this part is part of the solution set. Then I move over to the next equation and let n equal to 0. Well, sine of pi over 2 is 1. Cosine of pi over 2 is 0, so that works. Let n equal to 0 in the last equation here. Well, sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0, so that actually doesn't work. That's extraneous. So the general solution set can be written as x equals to pi plus 2 pi n, or x equals to pi over 2 plus 2 pi n, where n is an integer. Okay, and this next equation, you can have your cheat sheet of identities with you. So sine of 2x is 2 sine x cosine x. And then if we subtract by cosine on each side of the equation to get 0, we can factor out cosine. And then by the zero product property, we can say cosine of x is equal to 0, or sine of x is equal to +1/2. So coming up with our general solution set here, we can think, okay, well, cosine would be 0 at pi over 2 and include all of the coterminal angles, or at 3 pi over 2. And then for sine equal to 1/2, that would be pi over 6 and all the coterminal angles, or 5 pi over 6 and all the coterminal angles. We do not have to check for extraneous solutions in this equation because we didn't square both sides. We didn't apply any identities that had different domains. Like, we don't need to check for any solutions that don't make sense. So that would be our general solution set. And then to solve for over the interval from 0 to 2 pi, you can either just solve the two equations, cosine of x equals to 0 or sine of x equals to 1/2 by inspection, or you can reference those the general solution set, and assigning values to n for each equation. So it's probably the most efficient to just think about solving by inspection and going, okay, well, cosine would be equal to 0 on that interval at pi over 2 and 3 pi over 2. And sine would be equal to 1/2 at pi over 6 and 5 pi over 6. Okay, this equation, well, cosecant is 1 over sine. So I could rewrite this as sine plus 1 over sine equals to -2. And we could think about multiplying by sine on both sides of the equation. so that the left-hand side becomes sine squared plus 1 equals -2 sine. And then to get 0 on one side of the equation, and then thinking about factoring. Okay, well, that's actually a perfect square trinomial. So we would just get sine of x equals to -1/2. It looks like we're not given an interval, so just coming up with the general solution set. Well, there's only one angle from 0 to 2 pi that would make sine equal to -1/2. So that would be 3 pi over 2, and then we need to include all of its coterminal angles. Okay, so this equation, we have sines and cosines. So oftentimes you need to use identities whenever you have an equation where you have multiple trig functions involved. So we want to be able to write this in terms of a single trig function. Since we have that Pythagorean identity, the sine squared plus cosine squared equals to 1, we can replace sine squared with 1 minus cosine squared. And then if we distribute that 2, and I'm going to rewrite this as 0 equals 2 cosine squared minus 3 cosine minus 2. And now we have a quadratic-like trig equation here where we can try and factor. I believe that would be -2 there and +1. Yes. So we get cosine of x equals to -1/2, or cosine of x is equal to +2. So for cosine of x equals to -1/2, coming up with the general solution set, cosine would be equal to -1/2 at 2 pi over 3, and then adding 2 pi n to include all the coterminal angles. And then also in quadrant 3, that would be 5 pi over 3. Oh, wait. 4 pi over 3. Sorry, 4 pi over 3. Just making sure I didn't make a mistake somewhere else. Okay, and we can say where n is an element of the integers. Now for cosine of x equals to 2, 2 is outside the range of cosine. Cosine oscillates between -1 and 1. There's no solution to that equation. So this ends up just being our general solution set. And then for solving from 0 to 2 pi, it would just end up being this values when n is equal to 0. So for all of these, we did use inspection. We solved by inspection, whether it was a more complicated argument or not. And then we also used some properties of equality, some other algebra techniques like factoring or squaring both sides of the equation. But most of it was solving by inspection.